If you are coming not from American system of education, you will find out sooner or later that American education loves real-life problems. I was taught for 6 years, a bachelor and master's degree in pure math with zero applications in anything. Speed, velocity, who cares? Let's do some, Taylor series and convergences and proof theorems and stuff. And then you come to America and they do applications already in 5th grade, 9th grade, and so on. So 2.7 is the most applied chapter in this class. 2.7 is related rates, and we're going to do it again in calculus 3. It's going to be multivariable related rates. But this homework will have basically almost no math, that just math and says find that. It'll be English, 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 math. English, English is just number, English number, English number. And you have to figure out what's happening. So international students or ESL students, English is a second language. You'll be struggling the most, just letting you know. And I'm teaching the way to help you to read fast. And for the exam, I don't create a new problem for the exam like other instructors tend to do. I copy one from the homework, so I know you've seen it before with the same wording in the same order, because I know if English is not your first language, it's just very struggling to translate it while everyone already solved it. It's just the most frustrating part of it. I clearly remember being upset. Everyone already moved on. I'm still translating what the heck we're talking about. So we're going to have some fun examples here. Right on the steps, I already put them on the screen, but you don't have to follow them. However, it's the best way to do it. First of all, when you approach the application of the real-life problem, you have to read it. Well, yeah, that's when you need to read the problem. So read the problem carefully. Sketching a picture will help you a lot. Sketch a picture. So you will have some shapes. Picture. You will have a triangle or a circle or a sphere. And that's why some geometry will show up, your favorite subject, geometry. So this picture will help you. Then you will have to identify related rates, which that's basically the new topic. The rates that are related through the third dimension. We're going to do mostly time in this class, but in multivariable calculus, it's going to go farther than that. So that will be very interesting to explain you how everything is related through the extra dimension. So you will have given, who is texting seriously? Like my mom is texting me right now in Telegram and I'm not replying, right? So better you don't reply either. So given, something is given and something is unknown. So you need to identify which one is given, which one is unknown. And then this solving part starts. So the most important step is to write down the equations. That comes from reading. When you read, you have to make sure you understand how everything is connected. Write equation maybe serial, that connects variables what you have in front of you. Maybe it's the equation of this circle or triangle or anything else. And then the solving part starts. So this is where everything starts to be solved. Differentiate. And to differentiate, we're going to use implicit differentiation. That's why this topic always comes right after implicit differentiation. For you to know, this order of material is taught everywhere in America. Implicit differentiation related rates, literally in every school from Harvard to University of Mexico, Florida, everywhere. Implicit differentiation. Then you plug in known values. Yeah, variables, values. So you only plug in after you differentiate. That's going to be important. Solve for the unknown and you get the answer. Extra step is for engineers, physics major, check the units. What if your answer doesn't make sense? What if they ask you like how fast the balloon is growing and you get -5? So just make sure it makes sense. But also how fast the woman was walking away from the pole, you will have that problem with the shadow moving, blah, blah, blah. And you get to like 100 miles per hour. That also doesn't make sense. So check some kind of intuition, which is again hard for foreigners because when I get some answer with feet per miles, I still don't have a feeling what is that. I know kilometers and feet per miles. So I tend to give weird examples in class with something like 37 feet per mile a person is walking. You know, like look at people. Does that make sense? People are like, no.
What are related rates?
What?
What are these?
So yeah, let's learn how to what related rates are. A chapter is called 2.7 related rates. I always give example with the very cool tree example. Other examples are very classical tree example. Other examples are very classical. To be honest, if you're stuck with this homework, you know what you should do. You post on the forum, and then you know what you should do after that. You Google. 99% of the problems from your homework are already in the internet. I solved many, but they're so classical. This woman with the shadow and the balloon. There's the ladder falling down from the wall. When I'm saying those problems, a person, again, from a university somewhere in New York, and in California, and in Texas, they all recognize what I'm saying. The shadow one. Yeah, so they're all very classical examples made up by Stewart, Book, or others. I like to introduce with a tree. So draw a nice tree. Try your best. Here's like a tree. Bloop, bloop, bloop. Remember, this is a psychological test when they ask you to draw a tree, and then you're being judged by everything. Like, do you have leaves there? So when I was a kid, I would always draw a little hole and little owl inside. And then some apples, la. You don't have to. That has nothing to do to the problem, actually. Here's your tree. And then here's the problem. So, tree example. We're going to explain what related rates means. So the tree is growing. Who is yawning? I just started. So seriously? The tree is growing. And then with time t. Let's go time t. At the same time, something else is growing. What do you think it is? So the tree is going up, taller and taller. What else is growing?
Fruit.
The fruit are growing. What?
Its shadow. If the sun is like oblique, its shadow.
The shadow is growing. They don't think about that. The trunk. So there's lots of things growing while the tree is growing. That means growing. That means how fast something is changing. The height is changing. The shadow is changing. The fruits are changing. The trunk is changing. Those are rates. And you know what? They're related because they are related with this tree and time. They're related through the dimension of time. So let's choose one, which is a trunk. At the same time, the trunk is growing. I'm choosing this one because I have formula that connects height and a trunk. The trunk is growing and also growing. And also with time t. With time t. So we have two things happening, changing. There are two changing behaviors. Something is growing. Something is growing. But then these two things are different. The tree is growing up, that's the height. And the trunk is growing, and trunk is not growing up. It goes to the width. So let me write down that it's the height. Height of the tree is growing. So this is how I'm first connecting related rates. Two rates. Height is growing, trunk is growing. When something is growing, it means it's changing. Changing means derivative. Let me write down. Changing means derivative. Derivative means rate. So we found two rates, and they're related through the time. So the chapter called related rates. So I actually Googled, and in Wikipedia, I found a formula, some very random formula of a tree. Height of the tree equals 3/4 radius of the trunk of the tree raised to the 1/2. So I found it in Wikipedia. It's not for all the trees, but I think it was for apple tree or something like that. Some classical trees where R people are already yawning. Radius of the trunk. Radius of the trunk. Here it is. So again, it's not just like a stupid problem from homework, and I don't call homework problems stupid, but I actually like found this. So I modeled basically. I decided to model myself some kind of interesting problem for students. And I Googled if there any relationship between the height of the tree and the trunk of the tree. And I found it literally right away in Wikipedia. And that's how science works. You just kind of Google and search things, and then you find a book or Wikipedia or articles and figure it out. So, when the tree is very tall and they ask you, so how fast it's growing, you know what you do. You know what derivative is. It's rate of change. You take change today, tomorrow, in the months, in the 3, and you have now lots of changes. And from lots of changes, you do the formula, right? y2 minus y1 over blah, blah, blah. Many, many times. And that's how you find instantaneous rate of change. Average rate of change will be what? 30 centimeters per month. But that's average. But then you can shrink the time and find the derivative to know how fast it's changing. Why do you need to do that? Because you want to predict how tall a tree will be in 7 years. For example, when it will reach your roof and then you have to move the roof or something like that. Or when it's going to reach the electricity wires and you need to actually trim it. You can predict that. So my question is, that if you need to know how fast the tree is growing, it's kind of complicated to measure the height of the tree. It'll be easier to measure the diameter of the tree, right? And then use the formula. That's exactly what I do here. Measure the diameter, divide by 2, or measure circumference, find r from there. Take a square root, multiply by 3/4, and you get how height the tree is. Isn't cool? So it makes sense. Actually, I knew a student in the plant major who was hired to go to little place, they have trees, and measured 200 trees, and he got money for that. So there's a whole study about it. Now questions. Question 1. Do I have questions here? No. Question 1, Q1. Well, let's find how fast does a tree grow. How fast does the tree grow? How fast does a tree grow? With respect to, and that's a very important phrase over here, I will put it in pink. With respect to, from now on I'll be using American abbreviation WRT. With respect to R. With respect to R. R of the trunk. Question mark. That's a radius of the trunk, not trunk. How fast does the tree grow with respect to trunk? Do you know what they're asking? They see this formula solution. Let me mark this formula to be a star. That's also very common thing to do it. So answer from the star. No, let's do the star now looks like this. And I'll rewrite it as H. Let me put it in green. H equals 3/4 R to the 1/2. That's what they're talking about. They see two variables, H and R. So they ask me how fast does the tree grow with respect to R. So does it mean we do what? Anyone just say it out loud.
DH, DR, DH.
Then we find DH, DR.
DH.
So actually that's the confusing part. So that will be important to explain. Then let's find H prime. H prime. And in this case, we only have two variables, H and R. And also the way how the phrase,
The change in H over change.
yeah, the phrase is telling you how fast, remember what it is? That's derivative. But how fast what? The tree grow. Okay, so that's H prime. That's how you read the problem. Well, H can be depending on different variables. So with respect to what? With respect to R. Oh, so that is DH, DR. This is the chapter when it actually matters to know the difference. Let me move it lower. H prime is how fast the height is changing. With respect to what? With respect to radius. What's the answer? 3/4 times.
1/2.
1/2 goes down. R to the,
Do R by
and then you simplify, right? So you can simplify to 3/8 r to the negative 1/2, or 1 over square root of r. If you want that, I don't mind. 3 over 8 square root of r. I like the previous answer more, but whatever. Good. So you see, r cannot be 0, makes sense. Why would r be 0? It's a radius of the tree. r is 0, there's no tree. So you cannot divide by 0, you see that. r cannot be negative, it's inside of the square root. It also makes sense, radius not supposed to be negative. So you see this calculation here makes sense. You should check that at some point, yeah.
Is there a math reason you're drawing R's like that, or is that a cultural thing?
My handwriting?
Yeah.
How do you draw R? I do like this. Oh, no, not like that. My R is like this. Is it the bad R?
It's just because in English it's more of like just a.
I remember, right? It's like this.
Yeah.
Yeah, there's no way I can change the habit anymore.
Yeah.
I changed, I mean, unless you really want me. But last time when students complained about my X, it took me 1.5 years to change the habit. It's very hard to change habit when you do something from like 5th grade or less. Or like, no, in this case, this is my alphabet. This is H in our language. So that one I do since what, 4 years old? I changed it, that was really good. But R, I would prefer not to change. Yeah, okay, thank you for letting me know. So,
Variables are variables.
R, like this, right?
It's fine.
It's fine.
I think you just wanted to make sure it wasn't like a math symbol, like a lamp.
Yeah, that's why, I think that's why they're asking. Yeah, good job. No, good job. People should point out. Yeah. I'll let you know when will be like a math.
And
Yes?
How many related rates will we be expected to do at once? Or will there be like a question that's
Let me finish the easy one first. Let's see. Yeah, the question is how many related rates we'll have. We did not even do yet related rates.
Will there be one that's like the tree grows with relation to the width of the tree, which is blocks the sunlight, which reflects.
Not
the
really,
graph,
but your
graph
homework will
grows.
show you. Your homework will show you how deep they want you to go. So, this is the first question you can ask. Why did we do it? It's not very hard. But now, let's do that. How fast, and I'm going to repeat the question so you can write it down here. How fast, but now it's going to be how fast does the tree grow? So the same thing, right? The height. The tree grow. And the only difference will be, let me put it in pink again, with respect to time t. With respect to time t, question mark. And that's the big difference here.
You didn't give us the equation for rate.
Let me finish. I think you're spoiling every next step I do. No spoilers alert. Let me do it. Yes, you're predicting my next step. So, this time is something different. It's not the same question anymore. They ask you, let's read it again. The first question is how fast, the first part, how fast, that's derivative. What? The tree grows. Okay, that's h prime. I still know it's h prime, nothing new here. Let me put it below. H prime. And then it says with respect to time. Like, okay, well that means it's h prime, which means dh dt now. So let me write down dh dt. That's interesting. So I need to find dh dt. Now, answer. The formula is star. Now we need to go and remember that star had some t in it. H depends on t. 3/4 is a constant. Parentheses. R depends on t because that's the width of the trunk to 1/2. That's now a new formula here. That's not new. We're rewriting the same formula, but we're adding extra dimension into it, which actually we're making chain rule out of it. And that's why chain rule was taught before that. So let me explain to you again through the graph. The graph looks like this. Here's my x. That's basically, let be a width. You can put it in the center or you don't have to. But say this is the center. And then I go up and it's going to be h. So x in this case is my radius. X will be what? Centimeters or something. So radius is over here. This is my radius. Say centimeters or inches. Height also, centimeters or inches, I don't care in this case. So we're talking about this trunk and the radius of the trunk. The tree is growing to the width and to the height at the same time. And now they're asking me, no, I don't want to see the relationship between height and radius without time. Because then it will say, if radius, do you know what this answer meant? That's actually probably important to mention. What does this answer mean? That all this equals to dH dr in the previous case. That means if I add r, if I calculate the change of r, say it was 20 centimeters, then this will be a change in height with using this formula. So a little bit of change in x give you a little bit in change of y, input and output. So they don't want this. What if I want to have t as a third dimension and I want to see not with respect to radius and height how it changes. I don't want to keep measuring trunk all the time to know the height. I want to have time. How tall the tree will be in January, in February, in 10 days, in 5 days. That is a different question. That means I need to dive deeper into this formula. Then h prime now is dh dt. Let me make it yellow. dt versus we had dr. And that's slow. That's the only small introduction to multivariable calculus before calculus 3. That means we're going to differentiate it this way. 3/4 is still there. 1/2 still goes down. R of t still to the negative 1/2. And then chain rule says times, and that is chain rule, times the derivative of the function inside, r prime. And to be consistent with dh notation, we're going to do dr dt. And I'm going to put in the squares. One rate has another rate in the equation. Those are your related changing rates, like so. See?
Yeah.
Yes?
Then how in the previous question we can just simply get rid of the t, and like in this question we are using t.
But it depends on the question. So it depends on what they want you to, I want to make a table. Depends on what they want you to find. And that means it depends on English. You have to read the question carefully. So H and R had a relationship with growing, and all of this depends on T. And like while I'm talking, the speed of my talking depends on T time, and you looking at it also T time. So everything relates through T. So to be honest, if you can figure out how T is part of the equation, and they ask you to differentiate with respect to T, you dig deeper. Here is my rationale for you to explain that. So
In the above equation, if we were to like answer t, then on the left hand side we have t, but on the right hand side we have t like root t.
Yeah. Root T? No.
But like how can we get rid of the t in the first equation, whereas in the second
In the first equation, it was not even there, you see? So let me show you, just a second. So the outside rationale is height. Here it is. Height depends on t. Like so. Okay, fine. Let's be a circle. Then the other rationale, let's make it a bit fatter because it's width. That is a trunk, radius of a trunk. And this one also depends on t. But they are together. Let me put it in some kind of rainbow, nice looking shape. So, several ways to ask a question about how fast something is changing. Am I asking how fast the relationship between these two are changing? Or am I asking how relationship is changing between these two with respect to time? Either ask them one with respect to another one, and you don't have to use chain rule. You ignore that there is any t at all. That's the idea. The A example was the first one, this example. There is no t. We don't care about any other variables. No gravity is used. Color doesn't matter. Soil, level of soil doesn't matter. Humidity. We ignored all of it. Just H and R differentiated, got the answer. And now the science comes into the picture and says, well, actually everything depends on t. And in calculus 3, we're going to say, well, actually there's a gravity involved. And actually the humidity is involved. And so on. Even distance between trees matters. and there's a tree above another tree, the growth changes, and so on. So, but actually chemistry of the soil is very important. Many students in engineering, they work on that if they choose to do that. Chemistry of the soil, and it's really fascinating how all this is important. In this case, you do chain rule. So if you have to dive deep into the belly, that's chain rule. Because it's chained reaction, or a function nested inside of the function. Yeah.
I still didn't get why we do not include the t in the first equation.
Yeah.
Because
Let's do it. Yeah.
if we do have h of t, we can still have r of t in the first equation, but not have the di by dt term, because that just be di by dr and evaluate to 1.
Yeah, exactly.
Yeah.
It's just going to be dr over dr, which is 1. Yeah.
But ma'am, the answer would change then.
Yeah, then but we still don't have the t in the brackets in the first equation, right?
Yeah.
With r, so I don't get that.
So the part is you looking at it from a mathematical point of view, and which is correct. But you should understand that even t depends on stuff. Let's say mu, viscosity, and then z, which is the third dimension. But somehow I did not write it down. But it's there. So the point is, every equation has deeper and deeper meanings into it, and you can go as deep as you want or not. The very first equation with no t in A, that's the very general shape. When we have only two relationships between r and h, it's like, and we're gonna do it right now, x squared plus y squared equals 1. That's a circle relationship between x and y in the circle. But don't you know that x also can depend on t, and then y also can depend on t equals to 1. Now, we have third dimension, and we can differentiate using chain rule with that to find how circle is growing and decaying with respect to t. We're going to do it right now. But then also you can include the viscosity of a balloon, say V, into both. And now the balloon has apparently material, and maybe gas matters also, or pressure. So you can add lots of variables in it, or you don't have to. So calculus 1 starts with no extra variables, just 2 dimension, and related rates adds 1 more to show how rates can be related through time. It's kind of...
If we use, if we solve the first question using t, the answer will remain unchanged.
If you do have t, so if you do have...
If you have something to plug for t, yes. But...
Okay, so if we did have h of t, we just have the same answer without di by dt. Because we still
if you plug in the moment, should be.
Yeah, because we're still differentiating with respect to r.
So the question is, the answer will be the same if we have dr dt given, and we can plug it in.
Doing dh by dr. Say we had h of t by dr. It just be 3/8 root of r of t.
Yes.
That's it. And then if you have dt, then it'll just be the same answer but with dr by dt, because we have...
And we plug it in. That should be the same. I would say on the graph, we have 2 dimensions here, r and h. We ask how fast something's changing. There's the graph. We found the slope. When we add a third dimension, okay, that's my last try to explain it. And if that's not enough, let's do it after the class so I can give another example. When we add third dimension t, it becomes a 3-dimensional picture now. Now apparently it's like a helicoid or surface or a sphere. And now we're asking the relationship in 3 dimension, which is still going to be the same thing, but in 3 dimension. And if it should be the same if you plug in t, a time, it changes with respect to t, then it shrinks back to 2 dimensions.
So
I can show you that better after the class if you want.
Okay,
Yes, just a second. Did you get it? Oh, yeah. 50-50. You both stay after class and maybe he'll explain you better. No, let's do it after class. Yeah.
So in the graph there, you plotted h in the y-axis and r in the x-axis, right? And usually when you differentiate, you do like dx over dy.
We usually do dy over dx. So we do output with respect to input.
Oh yeah, so
No, I know, that's a new notation. So it takes time to get used to it. Do you remember y2 minus y1 thing? So if you remember that, it follows the same notation, dy over dx. That's how it is, yeah. No, good question, yeah.
Because would it still be understandable if I changed those d's into deltas? Because that's just easier for me to remember.
It's not the same thing, unfortunately. Copy this problem for now while I'm talking. Balloon is growing. So, no, you have to use D. Actually, right, this week we're going to learn the difference between D and delta. It's 2.8, the last chapter. That's called differential, and that has something to do with approximations. Sometimes they mean the same and sometimes not, so we will have to figure out that.
So the D is instantaneous change and the delta is not instantaneous change?
The delta also used as little change. And little is not instant. Instant as a limit means goes as close as small as you want, while delta can be 0.00001. And that's why sometimes people use it as the same in computer science, but it's not the same mathematically.
So if I, is it correct to like think of DH and DR as their own type of variables and do the algebra with that?
Your question is so smart. Yeah, we'll do it on Wednesday actually. If we can do it separately, yes. On Wednesday we can do it separately as DH and DR.
Because it's the change in, so you can.
We're gonna, yes, exactly. We're gonna do it. It's gonna be delta H and delta R, and I will explain what's the difference. You're jumping ahead today. Your brain is like going forward.
Oh yeah, it's because I didn't notice this D has citric acid in it and it deactivates my meds.
I see. Oh, you see, it's good. Classical question which we like to put in the quiz exam, final exam, everywhere. Your social security number, this problem is everywhere. It's just very classical around the America. Say, people like delayed reaction. What did you just say? Do you know when we as immigrants come and they give us social security, right away, and they tell you don't tell anyone your social security, okay? And then for the next 3 months, everyone asked us for social security, and we had to give it to them. Our job, graduate school, and driver license. And like I was told not to tell anyone. I literally tell it to everyone for 2 months. It's the weirdest thing. So funny. I'm like, are you sure you guys asking me? Because I was told, yes, we are government. Give us your social security. The volume of a sphere of the balloon, spherical balloon, is given as. So in your homework, they will not give you these formulas, triangle, volumes, but on exam, I don't expect you to remember. So when my students in calculus 1, they stuck, how do you know? I don't remember the formula of the volume of the conical shape. I take my phone and like, okay, Google, what's the volume of the conical shape? And when we did it on Zoom, I activated all the Googles and the half of the class through Zoom. And then they told me that, so I did. Then I said Alexa, and then the other half of the class got activated. Yeah, mine activated right now. So you just search for the formulas. Again, you're a scientist. Search stuff. The question is, this is your homework, so see how to read it fast. I will teach you how to read it fast. How fast does the volume change when the radius is 10 if the radius is increasing at the rate of 4 centimeters per minute? Like this is when your motivation goes to 0 and you go watch a TV show. You need to learn how to read it fast so you don't get demotivated during the exam and you don't freak out. Because I think that's scary. That's too much English in my mind in the calculus class. So math and English, too much. Okay, the first thing I see is that English not as a first language speaker is how fast. How fast as derivative. I know that. So something they give me something. Or they ask me about something. When they say how fast, that's going to be a question. So we need to find something. How fast something is changing. Okay, that's definitely derivative. Now I need to find the noun or the object or whatever that is actually changing. So I'm going to put it in yellow. I see volume. Oh, how fast does the volume change? Good. This is good enough to write down. I will write down here. V prime, we don't know. And I don't know yet with respect to what. But I'm gonna at least know this is derivative of V and we don't know it. Then they say when the radius is 10. And then if the radius is increasing at the rate of 4. What? So let me go to the second phrase first. It's gonna be in blue. I see the radius is changing. Increasing, decreasing means changing. That is also derivative, right? That is the hint. And also in the previous class, I gave you synonyms of the derivative. How fast, a final instantaneous rate of change, and per, or the slash. centimeters per minute, centimeters per minute, miles per hour. That means derivative as well of something. Okay, so that is derivative. In blue, it's also derivative here. How fast, what? Radius is changing, increasing. So I will do r prime. But now this number is given. R prime is what? 4, and I will not circle centimeters. 4 centimeters per minute. And now I see per minute. Oh, everything is in terms of time. So I can start building my tiny table, which is thing number 1, dv with respect to t is not given. dr with respect to t is given 4. You can write down centimeters per minute, like so. And then as a student, you see one more number. And usually if there's a number missing, then probably we need to use it. So before we write it down the other number, those two are related rates. Here they are. One rate is given. Let's go back to my table. Sketch the picture. Okay, I'm gonna sketch the balloon. That's actually not very necessary in this case. Identify related rates. One is given, the other one is unknown. We did. Write down the equation that connects them. So I also see that there's number 10 is given. What is 10? R. It's not R prime. It says radius is 10. It doesn't say per centimeters, per miles, per minutes, per gallons. It says centimeters. So that is not a derivative. It also doesn't say radius is changing 10. It says radius is 10. That means R, I'll actually put it here. R is 10 centimeters. Fine, let me not be so dramatic. Centimeters, no circle. Does that make sense? So 3 numbers and we divided them into categories. So I found all of this. This is good. Now I can do the next step in my table. This is R prime. And how to write down nicely. And my table says write down the equation that connects them. So let me do it. This is R prime equals 4. And now we know it's V prime with respect to t and R prime with respect to t. Well, the formula that connects them is either given or you have to figure out. If it's not given, then they say, oh, it's spherical. Since it's spherical, I can actually sketch the picture. Here it is. It's a sphere. That's not a sphere. That's a circle. But you can add dimension to it and it becomes a sphere. Here it is. A spherical balloon is changing. And in this case, it's increasing. The radius is increasing. So here's my radius. So the volume is increasing. That's classical example. When you make a balloon bigger, 2 rates are showing up right away. The radius is increasing, the volume is increasing. And also the gas is changing. And also the surface area is changing as well. So some problems ask you about the surface area. And also the stretchiness of the material. That's also important. Blah, blah, blah. You Google equation of the volume that connects with t time 4/3 pi r, that depends on time cube. That's the volume of the sphere. And now you start solving. So this is for now are my steps. Let me move away this. What do you think about this before I move on?
Can you just tell the answer once?
What? What do you say?
Answer of this question.
Yeah, we're getting it. We're gonna solve it. Yeah, we're getting there. So we're gonna now start. So we're gonna have, I would say, like solution. I need to find this dv dt. I'm doing implicit differentiation on everything I see. So 4/3 goes down. Pi 3 goes down, r squared of t. Something is missing. When I'm differentiating everything with y prime pops out. That's what I was saying in the implicit differentiation. Same thing here. Because r depends on t, we need to have answer that everything has dt at the bottom. So where is my r prime? It should be at the very end, dr dt. Here are my two related rates. Here they are, related rates. They are rates and they are related through the third dimension t. Related rates, like so. And I will, this is my formula star, just a new one. So if you want, you can call it star now. And also you can simplify the 3 and 1/3, but that's not the most important. The next step is the most important. The next step is plug everything they gave you only now. You can't plug 10 right away into R. You need to plug it when you have derivatives. So let me go back to steps. Step 1, read the problem, sketch the picture. Done. That was a sphere. Related rates. Done. We figure out the R and dH. Equation, that's the volume. Done. Differentiate everything using implicit differentiation. Done. So step 5. That's already step 5. Plug in the numbers. Let me write down step 5. Step 4. Step 1 is a picture. Step 2 are rates. And step 3, R was given. You don't have to, the steps not important to me. It just kind of organizes the thought, I think. But I'm not requiring you to follow the steps. So you plug all the known numbers. They might be more than one. R equals 10. Now you plug. And you get dv with respect to t, dv dt is 4 pi. And then R is 10. And then you cube it times dr with respect to t. And now the answer follows from here, step 6. Step 6 says solve for the unknown variable. And now it's interesting. I can ask you to find dv dt or dr dt. There are two rates here. And in your homework and exam, did I make everyone like raising hand? That means there's a mistake. Just say. And everyone is, oh, the square?
I think it's square now.
Thank you. Good catch. Yeah, I saw people like, if people raising hands, probably something is wrong. So I can ask you to find the HDT on the exam and on the quiz and on the homework. You will have both questions. I know that they're asking me to find dv dt. Okay, that means it's the left-hand side. dv dt is the one I need to find. So 4 pi. Actually, that's kind of extra step. Instead of dr of the dt, why not to plug 4 times 4? Let's not have extra steps, I just realized. Plug r equals 10, and then dr, no, it's gonna too small. We plug r equals 10, and dr dt was 4. Plug these two. So that's now easy. And the answer follows is going to be what?
1600.
1600. Careful, calculate 1600 pi. You can calculate approximately what pi is, 3, 14, 59, and so on. But the exact answer is always the best. So if you're stuck in Webbrook, you know that's probably your fault. Just have exact answer. One more thing, there's an extra step 7. Step 7 says, check if it makes sense. Well, we know that can this rate be negative, by the way? What do you think? Can it be negative?
Yeah, if the balloon is deflating.
It can. Derivative negative means the original function is decreasing. So, for example, balloon is deflating. Then it would be negative. But we know it's increasing. It says that in the problem. It says is increasing. So that's why it's positive. So is it increasing or decreasing? Increasing. Why? Because derivative is positive. Either you know its effect or derivative tells you that the original one is increasing. Yeah? Oh, let me show you here. The question is step 4 and 5. T is 10. We plug it in. It was given. And this one is also given. It is 4. So given, I will put it in green. Given. So we give you usually 2 or 3 numbers and you plug them all after you differentiate. Thank you for asking. Yeah. Just like, yeah.
How do we know if the question
You have to read. So my second question changes the order. Check it out. How fast does the radius change? That's the R dt. Oh, that's a good question too. They're asking it here with respect to minutes. So it will pop out at some point per minute. If they say, either they say with respect to radius, then you know it's the easy one, or usually in this chapter they will not do the easy one. They will do always the per time. But you will see it in the problem. Yeah, exactly. We don't know, yeah. But you know what I want to say? Lost my thoughts. The per or how fast it changing, the units they show you. The units shows you how deep we're digging into the equation. Oh, good question, yeah. Good job, people, good questions. Watch my other videos, I have lots of solutions. Let me see. Falling sand, I have that. And the leather, yeah, the shadow person. I have solution of this one too in the videos. The woman, 6 feet tall woman.